Good evening, everyone. Welcome to week 3 live interaction session for the course Waste to Energy Conversion. So let's just wait for a few minutes for others to join before we begin our session for today. So let's begin our session for today. Can anybody please confirm whether my voice is audible? Hello? Oh, okay. Okay, fine. That's not an issue. So let me just share my screen. I hope my presentation is visible. So, welcome everyone for the week 3 live interaction session for the course Waste to Energy Conversion. This course is offered by Professor Prasanajit Mondal from the Department of Chemical Engineering, IIT Roorkee, under the NPTEL SWAYAM program. Myself, Pratyumnan, a PhD research scholar at the Department of Chemical Engineering, IIT Guwahati, Assam, is responsible for conducting the live interaction session every week. So we have come across two sessions. So we are in week 3. So in the previous 2 weeks, let's just recollect what we have learned. So in the week 1, we focused on the introduction of waste material. What are basically waste material? Their specific, their definition, and we saw on the characteristic properties of the waste material. So we focused on the introduction basics of thermochemical routes, so where we discussed about three different types of thermochemical conversion routes. One is the incineration, second one is the gasification, and then the third one is your pyrolysis process. So this was continued for the week 2 as well. So there we focused on understanding each process in detail. So we discussed about incineration, what is the mechanism of incineration, and then we shifted our focus to the different type of incinerators that is used, and then we moved on towards gasification, the different types of gasifiers, and then their application. Also we solved I hope a quite variety of problems. So we ended our discussion on gasification last week. So we continue our week 3 live interaction session from there. So we discussed about gasification process. So here in this live interaction session, we will discuss on gasifiers which are used for this gasification process and the entire details of the pyrolysis process. So before going into this details, what is, again, this we have discussed last week also. So what is the primary difference between incineration, gasification and pyrolysis process? Yes, anyone? What is the primary difference, or you can say what is the difference in the reaction conditions that basically classify this process as incineration, gasification and pyrolysis? Something related to that R value, if you remember. Mm. And in gasification, you have, yeah. And in incineration, you can say uncontrolled or excess supply of air. Yeah. So again, we had the classification based on the R value, which is nothing but the oxygen to the what do you say, the fuel ratio or the waste material ratio as 2 point greater than 0.68, less than 0.68, 0.68 to 2.5 if I'm not wrong, and then greater than 2.5, and based, yes. Okay, so based on this process, we classified the thermochemical conversion routes as incineration, gasification, and pyrolysis. So this just to recollect. So today here we discussed about the different types of gasifiers. So I hope you will be able to recollect what are the different types of gasifiers that was discussed in the course. Any so is anybody able to recollect what are the different types of gasifiers that was discussed in the lecture? So starting with we have this, yeah, and the another one is entrained bed. Huh. So these three have certain advantages and disadvantages. So we have a clear distinction on the basis of the reaction temperature, the temperature of the gas outlet, and then the most specific is that the syngas quality. So if you see in case of the fixed bed, the syngas that gets generated is kinds of contain it contains tar and phenolic compounds. Whereas in case of the fluidized bed, if you see that syngas basically contains tar and char. So tar as well as char is present. However, in case of the entrained bed reactor, the syngas quality is kind of more superior. And by superior, what I mean is that the presence of the tar as well, so no tar is present, and then the methane is also, that is CH4, is also present in very minimal quantity. So this is one of the major important difference with or major important, yeah, kind of difference when you do this gasification in fixed bed, fluidized bed, as well as that of the entrained bed reactors. So if you see another one major difference is that compared to fixed bed and entrained bed, the fluidized bed reactor operates at a much lower temperature. So if you remember, if I remember correctly, the temperature range, that is the temperature in the combustion zone for your fixed bed, is around 1500 to 1800 degrees Celsius, and in case of entrained bed it is around 1400 to 1600 degrees Celsius. But if you see for that of the fluidized bed, it's around 900 degrees Celsius. The major reason why the temperature is so low in case of the fluidized bed is because, as we discussed in the previous session as well as in the course, the heat transfer rates in case of the fluidized bed is comparatively more. So since that heat transfer is more in the fluidized bed, so higher temperature is not required. So that is one of the, so at lower temperature itself, due to that much efficient heat transfer, that waste material is able to combust. So that is one of the major advantage of the fluidized bed, because less temperature means lesser amount of energy is required to is required to supply to produce that heat. So the fluidized bed, what do you say, gasifiers are not energy intensive, so they basically consume much lesser amount of energy for the generation of the temperature in their combustion zone. So in fixed bed we have two different types. One is your updraft and another one is the downdraft. So can anyone tell me what is the basic difference between this updraft and downdraft gasifiers in fixed bed? Mm. And in case of the downdraft gasifiers? Mm. And then the syngas, whatever gets produced, is also collected from the middle, yeah, from the bottom. So if you see in case of updraft, you can call. So as somebody rightly said, there is the biomass is fed from the so sorry, biomass in the sense the waste material is fed from the top, and then the gasifying agent, or you can say the oxygen, is fed from the bottom. So there is basically a counter current flow between the biomass as well as that of the gas. Whereas in case of the downdraft, there is a the flow of the biomass as well as that of the gas is in the same direction. So because of this difference in the flow direction between the biomass as well as that of the gas, the contact between the gas as well as biomass is going to be altered. So in case of the updraft gasifier, if you see, since they are in the counter current flow, the contact between both this biomass as well as that of the air will not be that much proper. So you can call it as a poor contact between the biomass as well as gas. So since there is a poor, what do you say, contact, not much amount of the material is going to be, what do you say, combusted in case of the updraft gasifier. So since if, so let's go by this way, if poor contact is present, and then if the process is not efficient or the combustion is not efficient, so this will directly affect your syngas quality. So in case of the updraft gasifier, the syngas has tar which is greater than 25 percentage. So more amount of tar is, is present in case of the syngas which is produced from the updraft gasifier. Downdraft gasifier, co-current flow or concurrent flow. So better contact. So better contact means better efficiency in the combustion process. So that gets directly affected in your syngas quality, which basically contains lesser percentage of tar. Of course it will contain tar. It is not like that of the entrained bed where the percentage of the tar is almost negligible, but compared to the updraft gasifier, downdraft gasifier has a lesser percentage of tar. So this is one of the main points to remember, because and as such the reason why we are specifically discussing is because if you see, again I want to reinstate this, if you see your assignment questions, majority of them are kind of very conceptual. So by discussing this once again, we try to recollect, and hopefully in this process we are able to remember these kind of concepts, so that it will be helpful for solving your assignment questions. So I hope assignment 1 and 2 went well for all of you. So yeah, that is the major reason for me to discuss the course content, the important, no, so what I feel important, that once again. So in case of, so this is about the fixed bed, downdraft, updraft, two types, and the difference between both of them, and then how is it affecting their syngas quality. So yes, here I just want to ask again one thing. I'm talking about this term called syngas. So how many of you know what does the syngas mean and what is the composition of the syngas? Actually, syngas is short form of something else. Yes, any answers from anyone? Yeah, so syngas can also be called as just a second. Oh yeah, yeah, water gas or synthesis gas, and then yeah, the composition is carbon monoxide and hydrogen. So this is in case if the what do you say, if you burn that waste material using oxygen. So if the percentage of, suppose let's say that the oxygen content is less, or or it's not a pure oxygen, you also have a considerable portion of nitrogen, then what you will call this? Producer gas. So if the percentage of the nitrogen is increased, then we can call it as producer gas. And I hope you know assignment 2, I guess one question is based on this concept. So yeah, so moving on. So we were discussing about the gasifiers. So next is the fluidized bed gasifiers. So in fluidized bed we have two different types. One is the bubbling and another one is the circulating. So here what is the basis of this classification? I mean, what separates a fluid, what basically distinguishes a fluidized bed as bubbling fluidized bed and circulating fluidized bed? So it is the velocity of the gas that you send from the bottom. So if the velocity of the gas is high, then you can call it as a circular. So in case of the fluidized bed, you have different types of fluidized bed like bubbling, circulating, and then there are also others. So the basics of, or you can say the basis on which they are distinguished, or they exhibit that type. is based on the velocity of the gas that you are going to send in. So the third type of gasifier is entrained bed gasifiers. So again, as we discussed, the percentage of tar is going to be negligible in entrained gasifiers or entrained bed gasifiers, and the percentage of CH4 is also going to be less in this entrained bed gasifiers. So here in case of the entrained bed gasifiers, the biomass, your air or oxygen, and then the steam. So of course, for the production of synthesis gases, syngas, you also require the steam presence. Just a sec. So all these three, what do you say, raw, all these three are fed from the top of the gasifiers. So there is a better flow and better contact between the biomass as well as that of the fuel. And in case of the entrained bed gasifiers, the combustion zone temperature is also quite high. It's not like fluidized bed. Here we maintain around 1400 or 1500 degrees Celsius. So because of all these, what happens is the percentage of conversion or the efficiency with which the material burns, or you can say gas gets combusted, will be more. So because of this, the syngas quality will be superior, or it basically produces a syngas with a negligible tar percentage and less CH4 content. However, it has one of kind of, you can say, a limitation. So in order to basically use entrained bed gasifiers, you require a pre-treatment process to be done to your feedstock what you're going to send in. Like if I'm saying biomass waste or any sort of the waste, that kind of waste need to undergo some sort of a pre-treatment process before it is fed into your gasifier systems. So this is about the entrained bed gasifiers, or like in general about the conventional types of gasifiers that are used. We have another one type of gasifiers. Of course, as it is said even in the course, it is something that is not used commercially. It is basically used on, you can say, it is predominantly in the research stage. So that is your plasma gasifiers. So this plasma gasifiers is typically used only for hazardous waste materials. So what do you do in case of the plasma gasifier? Of course, it has a lot of advantages. So whatever kind of limitations that you have in the fixed, fluidized or entrained bed gasifiers, that limitation gets solved in if you use plasma gasifiers. You don't need to worry about the moisture percentage that is present in your feedstock, or you don't need to worry about the particle size, or you don't require any sort of pre-treatment process that is required in case of the conventional type of gasifiers that we discussed previously. So whatever may be the type of the feedstock, because of that high temperature that gets generated by the plasma, that process will be very efficient. So you don't need to worry about what type of material you are going to process, because once you use the two electrode setup, so it basically consists of an electrode setup and then you pass on the voltage. So because of that, what happens is that the molecules present in the gasifier will get ionized, and due to this, the temperature of the systems will keep increasing. So if you would have paid attention carefully to the course, the temperature what is uh, obtained through this plasma gasifier process is around 4000 to 7000 degrees Celsius. So that's approximately, you can say, 5 to 10 times higher than what you use in your fixed bed gasifiers. So this is a very efficient technology, but again, generation of plasma is not that easy. You require sophisticated techniques, so the process of setup is more compared to your other conventional gasifiers, and that is one of the limitations why this system is not something that is commercially used till now. So this is all about the gasifiers. Once we generate these gasifiers, we need to go for this utilization process. So let's just quickly go through about this syngas utilization. So carbon monoxide plus hydrogen makes something so called as a syngas. So this hydrogen gas is very important. So apart from that use of synthesis gas, this hydrogen, if you separate, it can be used for lot of other purpose. So like for example, using hydrogen production, you can go for power generation and many more use of hydrogens is available. So you can always check in the internet about the different uses of hydrogen gas, or what are the applications of this hydrogen gas that gets generated using during the syngas process. So this syngas as such, it is utilized in multiple process. One is the what do you say, to synthesize methanol and its derivatives. So using the syngas CO plus H2, you can derive methanol and the other derivatives. Of course there's a big list. You have this dimethyl ether and many more compounds which you can generate through this syngas process. Of course you require a typical certain reaction conditions as well as catalysts, but you can use the CO plus H2 to generate these kind of fuels, and you can also say it as biofuels. And then you can go for this what do you say, FT liquids, so that is the Fischer-Tropsch synthesis liquids. Then you can go for the production of SNGs. So we will discuss about SNGs more as we go towards this what do you say, the assignment solving section. And then it is used for the generation of hydrogen. So that's what I said, hydrogen is used for a lot of power production. It is used in the turbine system. So please have a look over it. But again, for this utilization, there is a particular condition that the hydrogen to the carbon monoxide ratio should be 2. So please keep this in mind. The ratio should be 2 between hydrogen gas generation, between the H2 and carbon monoxide. That particular molar ratio should be 2. So this syngas can not be just used as such it is produced, so it needs to undergo cooling. Two different process, one is the direct quenching and another one is the indirect cooling. And then after that it needs to be clean. So this syngas usually contain acidic gases, so that needs to be clean. So you have acidic gases like CO2 and H2S. So those need to be concentrated, and then we can obtain CO2 as well as H2S, and from there we can obtain the sulfur. So again, for this process there are multiple type of adsorption process that is used. So let's discuss that when we go to this assignment solving section. After this you have this pyrolysis process. So in case of pyrolysis process, the basic distinction is it happens in a controlled supply of oxygen or of air. So when that happens, when there is a limited supply of oxygen, majority of your feed or the waste material is going to get thermally decomposed. So chances of something getting combusted in this process is very less. It is not going to happen. Majorly it is only a sort of thermal decomposition process. So three things will be generated during this process. One is your bio oil, another one is a char, and then the third one is the gas production. So these are the three things that will be generated during this pyrolysis process. Of course, again you have many different types of pyrolysis like slow pyrolysis, fast pyrolysis, catalyst pyrolysis, and so on. And in case of this pyrolysis also, you have different type of what do you say, systems or reactors for this pyrolysis process. Again, if anybody is willing, they can list out this type of reactors which are used in the pyrolysis process. So we have this fixed bed, fluidized bed. Apart from that, we have this anyone who knows what are the other different types of reactors used in this pyrolysis process? So you have something like ablative, and then the screw, what do you say? If I'm not wrong, it is called the yeah, rotating cone, and then you have something called screw type. Yeah, vacuum pyrolysis. Yes, then apart from that, mm, screw reactors. I mean, you have this list, so you can go through the last two modules for the week three live interaction session. Over there, you'll be able to see, I mean, over there, you'll be able to learn each of this type of reactors. You can get a little bit idea on each of these different reactors that is used for this pyrolysis process. So let's just not end, but let's just keep this discussion over here for a while, and let's go towards solving some of the assignment problems. So whatever we missed while discussing in this introduction session, in the assignment section, I hope we'll be able to cover those. So let me just zoom in. So the very first question, which of the following is solvent is used in the Selexol based absorption process? You have three options. One is called methyl diethanol amine, dimethyl ethers of polyethylene glycol. It is DEPG, and then you have something so called as methanol. So this is something of the concept related to your hydrogen sulfide and the carbon dioxide absorption. So for concentrating your H2S and the CO2, you use absorbents. Right? In the syngas cleaning process, you need to remove these two, what do you say, gases from the syngas. So for this process, you go for an adsorption based system. Specifically speaking, solvent based adsorption process. So over there, you have this absorption process called Selexol based absorption process. So it particularly uses a solvent. Second option, ethylene glycol. So what about others? Do they have any different answers? So any different answers from anyone else? So it is dimethyl ethers of polyethylene glycol. Yes, that's right. But again, so as we always do, we won't just stop with finding the right answers. We also look for what does the other options also mean. So what about the first one? Like let's discuss about the details of this adsorption process. So methyl diethanol amine, so this is a solvent based adsorption, so this is basically used as a solvent. So what type of adsorption process does this what do you say, takes place or undergoes? Physical and chemical absorption. Yeah, but I am specifically asking for this methyl diethanolamine. Yeah. So the salt. So let me just write that here. So solvent based adsorption process, solvent based adsorption usually sorry absorption usually takes place either through chemical or physical means, either physical or chemical. Okay, okay, let it be like that. So as somebody rightly said, methyl diethanol amine typically undergoes chemical absorption. So what about this? So this dimethyl ethers of polyethylene glycol, this Selexol based adsorption process. Yeah, physical absorption. And what about this third process which uses methanol? The name of the process first. Yeah, that is fine. But what is the name like? Yeah, rectisol process. Rectisol. Yeah, so this is called, so it is rectisol based, rectisol solvent based adsorption, you can say. So this, each one of them has their own characteristics. So if you see this methyl diethanol amine, which goes through chemical absorption process, what is the temperature at which they operate? So these processes, these three different processes are classified also based on their temperature. So what is this temperature difference? Or I mean, yeah. So diethanol amine. So you can call it as ambient conditions, or again 30 to 35 degrees Celsius makes sense. And then you have your physical absorption process. So these two, so rectisol also is a physical absorption process. So these two process typically happens at temperatures below 0 degrees Celsius. So temperature range is below 0. Here also it is below 0 degrees Celsius. But again, it is not that both it happens like exactly at the same temperature. The rectisol happens at a much more negative temperatures compared to the Selexol based adsorption process. So if you see this temperature range is around, if you are able to recollect, it is around minus 35 to minus 60 degrees Celsius. Whereas if you see this dimethyl ethers of polyethylene glycol or the Selexol based adsorption process, this usually happens at a temperature very, what do you say, close to 0 degrees Celsius, but again below. So minus 4 to minus 7 degree Celsius. Oh, yeah. Let me just zoom out a bit. Okay. So this is about the distinction in which the process actually happens. based on the way of mechanism of absorption, the temperature range at which it operates. So here, uh, everything is basically to concentrate both H2S as well as CO2, but one particular process concentrate both H2 as well as CO2 very efficiently. That is their concentration percentage, the percentage of H2S and CO2 that gets concentrated through this solvent based adsorption, or that gets absorbed through this process, is in the percentage of 98.5 to 99 percentage for both H2S as well as CO2. So which is that particular process which has such high percentage of you can say absorption among all three? So, in if you see, all the three processes are good in concentrating your H2S. Of course, they vary by slighter percentages, but in one particular, so H2S, it gets absorbed up to 98 to 98.5 percentages in all the three cases. However, the CO2 percentage remains as a variable, but there is one process among the three which has a CO2 percentage around 99 to 98.5 percentage, similar to H2S. So which is that particular process here? Is it your the first one with the chemical absorption, or is this Selexol one, or is it this Rectisol? Yes. Any idea on which process it could be? You can also type it in chat box if you are, if you if you are unable to, what do you say, if you cannot like speak out here due to some microphone issues or something, you are welcome to use the chat box. So it is the rectisol process. So here the H2S and the CO2, that percentage is approximately in the range of 98.5, sorry, to 99.5 percentage. So if you see, in case of this methyl diethanol amine, over there, yes, the H2S selectivity will be more compared to CO2, but then the CO2 percentage is around only 30. But in case of this rectisol, it's around both of H2S as well as CO2, it is between 98.5 to 99.5 percentage. So yes, this is about this solvent based adsorption process. So again, this process is like, you have your feedstock which is fed from the top, and then this solvent goes from the bottom, they come into contact, and then the absorption process takes place, and then the gas is released out, and then the dirty solvent is taken from the top. So yeah. So this is the process. So we are discussing more in detail because, again, as I'm saying, there can be questions which can come from, which can be just a little bit modification of the question number one. Like if you see question number two, I hope everybody will be able to answer it right now. MDA, methyl diethanol amine, is used for which type of absorption process? Physical, chemical, or both A and B? I hope everybody will be able to answer it right now. Yes. So others, so the MDA process is used for, Chemical absorption. Okay, one person has given. What about others? So the reason that I'm discussing, I'm actually repeating it once again. So by just doing one question in detail, we will be able to solve a lot of questions, a lot of similar questions very easily. So it's chemical absorption. Okay. I hope everybody is able to get it. If you have any kind of what do you say questions related to this, please let me know, because it is better to finish off that as in there itself. Any queries or any questions? Again, it's a very straightforward stuff. Oh, okay, okay, okay. I haven't gone for that question yet. So I'm still asking for anyone if they have anything related to question 2 before we jump to question 3. So, okay, you can always post your, if you have any question, please post your questions in the chat box. Now, let me move to question number 3. What is the particle size and the moisture content in the entrained bed gasifiers? So, again, you have three options, and here we are asking for entrained bed gasifiers. Any? Okay, we have received two response as option C. Yes, it is option C. So your percentage of moisture should be around 15 or 10 to 15 percentage, and then the particle size should be less than 1 mm. So this is for entrained bed gasifiers. That's correct. What about for the rest two? That is your fixed bed and the fluidized bed. Let me add one extra space here. Fixed bed, fixed bed, and you have next one is fluidized bed. So what about for these two? What should be the particle size and what should be the moisture percentage? Hmm. Okay, and for fluidized bed, 5 to 6. You mean 60 or 16? Okay. So I am going to write this as, please check the slides. Again, the particle size I'm very sure. For in case of the fluidized bed, it will be somewhere in the hundreds nanometer, and if you see in case of fluidized bed, it will be around 5 to 50 nanometers. But for moisture content, I'm sure in case of fixed bed, it will be somewhere around 10 to 60 percentage. But I'm not sure for fluidized bed, so I'm going to write here as, please check the slides. So likewise, you can actually get questions in your assignment. Here it is based on entrained bed gasifiers. You can have question, very similar question, wherein you will be asked to what do you say, comment on the particle size and the moisture content of fixed bed and fluidized bed reactor. So you can get questions of that sort. So it's better when to have a to remember for all the gasifiers what is the particle size and then the moisture content. So next question, I guess I'll shift this question to another slide. Just a second. Editable. So here you have your question number 4. Clause process is used for. So this is something. Okay, I'll not tell the answer because the question itself is a straightforward question. Clause process is used for recovery of elemental sulfur, recovery of nickel, and recovery of carbon. I think somebody has answered. Sulfur. Okay. Anybody else? Option E. Okay. So we have got some response. So yes, it is the recovery of elemental sulfur. Okay. I guess some other. So it is a recovery of elemental sulfur. So this is a recovery of elemental sulfur from what? Like where are we going to? From what source are we going to recover this elemental sulfur? Source of sulfur. Sorry. What is the source of the sulfur? Where are we going to recover this elemental sulfur from? Yes. Uh, like this. Well, that might be an answer, but here we are specifically discussing, related to this syngas. So, okay, let me concentrate the question further. So, this recovery of the elemental sulfur is going to happen from the syngas, whatever during syngas cleaning. What happens is there are some acidic gases also going to be present along with the syngas. So these acidic gases are absorbed just as we discussed right now. From there, from these acidic gases, we are going to recover this sulfur. So what is that acidic gas source? Well, that may be a right answer, but that is from a what do you say, a generalized broader perspective. But this what I'm asking is something that is related to the course. So we discussed about this with this absorption process. So we discussed about what do you say, mm, how far this different type of solvents that we discussed in this slide are used for absorbing these two components. So source of sulfur in case of this is going to be H2S, hydrogen sulfide, dihydrogen sulfide. So so from here we are going to recover our sulfur or get elemental sulfur. So again we need to discuss few things here. What is the, of course, class process is basically used for recovery of elemental sulfur, that's okay, but what is the reaction, or how is this H2SO4 is going to give us that elemental sulfur? What is that reaction process? Anyone have idea on that two reactions? So let me just write that. So I'll just give a H2S gives S. So this you, so you're supposed to convert this H2S to sulfur, elemental sulfur. So how you are going to do, or how, or what does the class process describe on converting this hydrogen on converting this H2S to elemental sulfur? The reaction. Just just keep thinking. Let me just check one thing. Okay. Okay. Mm. So that just to check whether the recording is done proper, is going on properly. So okay, let me just give the reaction. It is there in the lecture also, so you can also check there. So the reaction goes something like this. H2S, when you react it with oxygen, you will get SO2, sulfur dioxide plus water. So this sulfur dioxide again on reacting with this H2S, that is, it's not that the H2S is going, all of the H2S is going to react, some of them will remain unreacted, so that SO2 which gets produced, if it reacts with this excess of or unreacted H2S, you will get. So this is the reaction, and in this reaction, so this process will utilize a catalyst. That catalyst is Al2O3. This is the catalyst that will be used in this process of SO2 to H2, SO2 plus H2S gives 3 by 8 of Si, that is your elemental sulfur, plus 2H2O. So this is the class process which is used for the recovery of the elemental sulfur, and this catalyst is, it is better to remember, because there are questions wherein you are asked to, wherein they have asked you to state which catalyst is used for what process. So please remember, whenever you see any process which utilizes a catalyst, it is better to just remember what kind of catalyst is used in that process. So What you can do with this recovered elemental sulfur? Again, you're going to recover an elemental sulfur, or from or from H2S you are going to recover that sulfur. So what is the purpose, or what is the use of this elemental sulfur, or why are you going to recover this elemental sulfur? Uric acid and oleum. Oleum, yeah. So these are the two. You can say like whatever that SO2 gas that gets generated can be used for this process, and apart from that, that SO2 gas can also be used for recovery of the elemental sulfur. So moving on. So we have question number 5. Identify the most suitable option, which is nothing but, so what is the question is, the Fischer-Tropsch synthesis plant may be operated with what catalyst? Let me just keep the screen. There are three catalysts given: Fe, or iron or cobalt based catalyst, iron or nickel based catalyst, nickel or molybdenum based catalyst. So this Fischer-Tropsch synthesis is used, for converting the syngas to other derivatives. We have a response. Option A. Yeah. So this is iron or cobalt based catalyst. So as I said, this Fischer-Tropsch synthesis is used for the utilization of the syngas, where the syngas is converted to other form of the derivatives. Moving on, same type of question, but here it is related to the methanol synthesis from carbon oxides and hydrogen. So you have carbon, it is carbon oxide, so mostly it will be carbon monoxide and hydrogen. If they combine together to form methanol, what kind of catalyst is required? Is it copper zinc, iron zinc, or copper nickel? Identify the most suitable option: methanol synthesis from carbon monoxides and hydrogen by which of this catalyst? Copper and zinc oxides. Yeah. So here we are not discussing for the other options, because catalyst can be used in multiple other synthesis process. So it is not possible to discuss or list out processes which may not be, you know, uh, within the scope of this course. So for these two questions, we will just identify the right answer. Question number 7. For low temperature methanol synthesis, which process is used? A. Methyl formate formation method. B. BNL method. So option B. So any other answers? BNL, yes. One person has. Any other answers for low temperature MEOH is methanol synthesis? Which process is used? A. Methyl formate formation method. B is BNL method. Which is the correct? Which one is correct here? Yeah. So here, well, that was a me. So here, both are correct answers. So sometimes you can have, in multiple choice question itself, you can have one or more than correct. So in some courses it is done. So that's the reason here. There was actually one more option below this as both A and B. I just neglected that option C, so I kept only option A and B. So yeah, so for low temperature methanol synthesis, both this process is used: methyl formate formation method and a BNL method. So what is this full form of BNL method? Yeah. So Brookhaven National Laboratory method. So, how does this low temperature methanol synthesis process differs from their conventional process? So, when you have something as low temperature methanol synthesis, something very specific where they mention the word low temperature, so there should be something very conventional also. So, how does the reaction condition varies in this conventional methanol synthesis and low temperature methanol synthesis process? The variation in the reaction condition. Difference between conventional and a low temperature methanol synthesis method. So one is the temperature and another one is the pressure. So what is the temperature in case of the conventional process, and what is the temperature in case of your low temperature synthesis method? You don't need to be exact, so you can just you know tell some, you can just state out an approximate value which you think might be correct. Okay, and in conventional methanol synthesis process? Hmm. Megapascal. Yes. So let me write that. So two methods. You cannot say so okay, fine. So we have conventional, and another one we have is low temperature synthesis. So in case of conventional, as somebody said, temperature is 220 to 250 degrees Celsius, and the pressure is around 5 to 8 megapascal. And in case of low temperature, it's around 100 degrees Celsius, and the pressure is around 20 to 25 bar. So this low temperature synthesis process basically happens at a happens at a considerably low temperature and pressure compared to this conventional methanol synthesis process. So this is the difference between their what do you say, the two processes. So in this low temperature, as we saw, we have methyl formate formation method and BNL method. So the whether anyone knows, uh, so let me just ask, what kind of catalyst is alone used, or what is the process in which this methyl formate formation method and BNL method works on? Just the process. So it is copper and alkoxide catalyst. So basically, you will first react the methanol with carbon monoxide to form the formate, and that will react with hydrogen gas to release methanol. So this is one. In case of your BNL method, you will have nickel and just a second. You will have nickel and its alkoxide catalyst. This will react on something called as triglyme, which is nothing but triethylene glycol dimethyl ether. So if so through these two methods, you will be able to generate methanol at a low temperature. So let me write the full: triethylene glycol dimethyl ether. Okay. So this is with question number 7. I hope there is not much doubt or any kind of questions related to this. So I'm going to question number 8. Let me take it to another page. What does SNG primarily stand for? Supernatural gas, substitute natural gas, specific natural gas. Again, this is also something related to this utilization of synthesis gas or syngas. SNG. So SNG is predominantly, contains or consists of your methane. What is the full form of SNG? Synthetic natural gas. Again, or you can say the substitute natural gas. Yes, synthetic natural gas is correct. It also has an alternate term called substitute natural gas. So this is something which is, you know related to the syngas utilization. So wherein the syngas is you know gets utilized in the form of or gets converted to this SNG, substitute or synthetic natural gas, and can be utilized, and again it's a natural gas. So whatever wherever we are using this natural gas, we can use this substitute or synthesized natural gas at those places as well. So there is nothing much to discuss in this. Let's go to question number 9. What absorbents are used in PSA for the removal of impurities from a gas stream? Silica gel, activated carbon, activated alumina. First of all, what is PSA? Let me see. Do we have? Okay, no one. So we have this three. What do you say? Kind of this multiple choice question, and then we will move forward for solving problem. Again, those problems are something that is what is left over from week 1 and week 2. What is PSA? So PSA means pressure swing absorption, and here the answer is going to be all three. So all okay. Do we have any response? Yes, one of the answer is silica gel, but if you but here you have all the three options as the answer. Silica gel, activated carbon, as well as activated alumina. All the three can be used as a adsorbent for this pressure swing adsorption process. So I would like all those who are here as well as who will be watching this video to really go and look at what is this pressure swing adsorption. I mean, what is the difference between the normal solvent absorption that we are doing and this pressure swing absorption? So this we will take up in the next class. I'll just have a little bit discussion. We'll have some sort of a little bit overview on what is pressure swing absorption, but I would like others to go and have a look over what is actually the difference between pressure swing absorption and the normal solvent based absorption process, or not any normal absorption process we talk about. So let's move on to question 10. Identify the most suitable option. Pyrolysis produce a straightforward char gas and liquid, and char and liquid. Which one among the three is the correct? The most suitable option. You can say pyrolysis produced what? Char and gas, or char, gas and liquid, or only gas and liquid? Yes. So all the three are generated in this pyrolysis process: char, gas, as well as liquid. So moving on, we have this final multi-choice question wherein the question is catalytic pyrolysis aims to reduce acidity, viscosity, and oxygen content, increasing the heat value, produce low carbon chain component, and now I am going to include one option as all of the above. Catalytic pyrolysis aims to reduce acidity, viscosity, and oxygen content, increasing the heat value or producing low carbon chain compounds. Do we have any response as answers? No. Yeah, all of the above. So that is the, what do you say, advantage of this catalytic pyrolysis process. Whatever that the pyrolysis process produces, it may have more acidic content, viscosity, or oxygen content may be more, and the heating value might be less. So by using this catalytic pyrolysis process, all these limitations are eliminated, so that the pyrolysis process as such becomes more efficient. So this is with the theoretical questions. So let's move towards problem solving. Yeah. So this was a question that we were discussing in week 1, but I guess at that time I did not receive any answers, so I just asked the attendees on that day to solve this question and let me know in week 2. But since due to time constraint we were unable to discuss this in the last week, so we are taken up. So that's the reason I just want to take up this question at least in week 3 so that we can finish it off. So the first part is very simple. So here we are asked to calculate the weight fraction of the moisture content in a biomass sample or biomass waste based on dry weight basis. Consider the weight before moisture removal as 9.23 and weight of biomass after moisture removal as 6.565 grams. So you are supposed to calculate the percentage of moisture content based on dry weight basis. So your basis actually matters. So here it is a dry weight basis. So what is the answer to this question? How much? 40.6. Okay, okay. So let me calculate and check. So the question 9.23 minus 6.565. 40.59 or 40.6. So this is the formula. So percentage of moisture content as weight of moist biomass waste before moisture removal minus waste weight of biomass waste after moisture removal by dry weight of biomass. Again, it is specifically I have given this dry weight because the basis is dry weight. So suppose if the basis is given as wet basis, then here it would be wet weight. So please be careful with the basis. So the second question is, consider a biomass sample of 6.24 mg. The biomass sample is heated to remove moisture. So we are asked to assume that 25 percentage is lost as moisture. The bone dry sample is burned to 1000 degrees Celsius to derive energy from the biomass waste. The ash is recovered after burning and its weight is measured as 2.53 mg. Calculate the percentage of ash based on the moisture free sample. So first here I will just give the direction. So first here you need to calculate the weight of the biomass or biomass waste after moisture removal. Based on that you need to calculate. I guess once you do that, I believe there is nothing else after that. I mean, it's just only division. Of course, please be careful that I have asked you to calculate the percentage of ash based on moisture free sample, and that is the reason I highlighted that. So what is the weight of the moisture? So this is for the first question. Let me just write the percentage moisture content is 40.59 percentage. Weight of the moisture. So they are saying take weight of the moisture as so 25 percentage weight of the sample is lost as moisture. So weight of the biomass sample we know is 6.24. Out of this 6.24, 25 percentage is moisture content. So I will just start writing it. So 0.25, 25 percentage, 25 by 100. So I'm writing it as 0.25. 6.24 times 0.25. 1.56. So 1.56 mg is moisture. So weight of the dry sample. What is the formula? Weight for if I know the weight of the moisture, how do I calculate weight of the dry sample? Is nothing but weight of wet sample minus weight of moisture. So that means weight of dry sample is 6.24 minus 1.56. So what it would be 4.68. Okay, let's calculate. Yeah, that's I'll just calculate 6.24 minus 1.56. 4.68. 4.68 mg. So this is your weight of dry sample. Now you need from here you need to calculate percentage of ash, which is nothing but, and this is moisture free sample, so it will be weight of ash by weight of, so will it be weight of dry waste sample or weight of wet waste sample? Yeah, because I have asked the question is directed towards calculating the percentage of ash based on moisture free sample, so it will be dry. So that is nothing but weight of ash is given as 2.53 by 4.68. So this times 100, 2.53 by 4.68. So it would be around 54.06 percentage. So this will be your percentage of ash. So any discrepancy with the answer, anyone have some? Okay, yeah, 54.06 percentage. So this is your percentage of ash based on moisture free sample. So these are the two questions which we were supposed to discuss in week 1 itself. So let me just give a minute or two. In case if anyone has doubts, please let me know or we can progress for the next question. Oh, that is some other question, I believe. Yeah, same week, but question might be different. Uh, yeah, so any doubts with that? Hmm. So fabric, but I guess I'm not sure who. It was just told as particle size. That is the reason I asked to go through that table. Yeah, so that 40 percentage excess air, we will be having one question very similar to that. I guess next question. So once I do that, I believe that we'll be able to solve that one. If in case if there is any difficulty, then we will take up in the next class or I will post the answer. So let me just go to the next question. So it is this question where we stopped last week. So we were given the municipal solid waste composition as so and so with carbon, hydrogen, oxygen, nitrogen, sulfur, chlorine, moisture, and ash. We were asked to determine the molecular formula, and we were asked to calculate what will be the composition of the flue gas or whatever that gas that gets generated after burning if 30 percentage excess of air is supplied. Then we were also asked to check whether that waste will form slag in the furnace or not. So if you remember, or you can also go back and check the recording in the YouTube. We calculated up till this molecular formula. We took 100 grams as the basis for the municipal waste, and then based on that we calculated the percentage of carbon, hydrogen, oxygen, nitrogen, and the other constituents. And based on the number of and based on that we calculated or we determined its molecular formula. And also based on this what do you say, the composition of the ash as K2O and Na2O, we calculated the slagging index and we obtained the value of slagging index as 0.3816, so which is greater than 0.34. So we concluded that this ash or the waste will certainly form a slag. So the virtual certainty of slag is there in this. What we left out was to calculate the composition of the flue gas in the system. So let's do that. So this was the formula. So here we were just to calculate the oxygen, the stoichiometric coefficient of oxygen. So let's do that. So I hope everybody is able to remember that we stopped here. So let's just continue from that place. So here nitrogen we determined as 0.0358. So that is from here. Yeah. So we determined the nitrogen, what do you say, coefficient as 0.0358. So since there is no other nitrogen that is here, it will be 0.0358. So now we are we are yet to balance only for this oxygen. So let's calculate that. So we already have a 2.86 with the biomass, the oxygen content as 2.86 with the biomass. So let me keep the stoichiometric coefficient as x for the O2 that we are going to supply. Oh, sorry, plus x is equal to. So now we are supposed to calculate the number of atoms of oxygen in your product side, or what you get in the flue gas. So that will be nothing but the number of atoms will be 3.52 times 2 plus 2.89 from your water plus 0.0358 times 2 from oxygen, or from NO2, plus sulfur dioxide will give 0.00625 times 2. Chlorine and ash, you don't have anything. So if we balance this, or if we solve for this equation, we will get the, here it will be 2x, because we are just balancing the number of atoms. So O2 is there, so it will be 2x. So let's calculate for this quickly. So this will be 7.04 plus 2.89 plus this will be around 0.0716 plus 0.01250. I hope my calculation is fine. This is fine. Let me just check for that. 0.0358 times 2, 0.0716, and this will be, yeah, so this is fine, minus 2.86. So 2x will be nothing but it will be equal to, so 2.89 minus 2.86 is 0.03. So that I'm just subtracting in my mind. I'm not going to use the calculator. So plus 0.03 plus 0.0716 plus 0.01250. So that will be 7.07. 7.1541. So this is 2x. So which means x will be nothing but 7.1541 by 2. So That will be around 3.57, somewhere around that. 3.577. So let me keep it as 3.57. This is the value of x. So let's replace this. Let me just copy this equation. So these many moles of oxygen is required, is the stoichiometric, what do you say, quantity of the oxygen required for this process. Now if you go to this question, we are being told that there is a 30 percentage excess of air is going to be supplied. So we have some stoichiometric oxygen, which we know that this much amount of oxygen needs to be supplied based on this equation. But then what is given to us is that with this you are going to add extra 30 percentage to it. So that will be nothing but, let me take all this calculation to one place. So which means, so 3.57 moles of O of oxygen is as per the stoichiometry, is as per stoch stoichiometry stoichiometry. So we are going to supply 30 percentage excess, so which will be nothing but, what is the point 3, so that is, so point 30 percentage excess will be 3.57 plus 30 percentage is point 0.3 times 3.57. So you can say this as 1.3 times 3.57. So that will be around 3.57 times 1.3, 4.641 moles, of sorry, oxygen is used. But here it's not just going to be oxygen, it is also going to be nitrogen, because it is air and not pure oxygen. I'm going to again highlight this. I'll make it bigger this time. Here it is not written only O2, it's also that nitrogen gas is going to participate. So if you remember, it depends upon the way you can assume in the course, in the lecture slides. If you see, it is taken as 4 is to 1. They have taken nitrogen as 80 percentage, oxygen as 20, or you can also take 79:21. So I am going to go what is there within the scope. So assuming nitrogen as 80 percentage and oxygen as 20 percentage. So if you see, the molar ratio will be around, will be exactly 4 is to 1. Again, here we are neglecting the contribution from the other gases because they are present in very negligible quantities. So these are, so the air predominantly contains nitrogen and oxygen. So that's the reason we are taking only these entities into consideration. So if we have 4.641 moles of O2, then how much will be nitrogen? Just a second. Okay. If oxygen number of mole, yes, 18.564. Okay, I have to calculate. So 4 times 4.641. Yeah, it will be somewhere around that value. So this times 4 is 18.564, 4 moles. Yes. So this is for the nitrogen content. So this nitrogen, whatever you are going to use, as I have previously said in week 1 also, this N2 gas is something which is going to be inert. So they are not going to participate within the reaction. So they, as such, they go in, they will come out. Now we need, so we are asked to calculate the composition of the flue gas. So let me take another slide. So what you need to do, what we need to do here is we need to calculate the total number of moles of the flue gas that will get generated. So we need to, so let me do one thing. I'll just copy this. So here it is going to be 4.641. Again, and then you will have this nitrogen content also, 18.564 N2. So this 18.642 will be here, 64 N2, plus whatever that excess of oxygen that we are taking in, we need to account for that also. So 4.64 minus 3.57, 4.641 sorry, 4.641 minus 3.57, 1.071. This much amount of oxygen will also come out. So now we need to calculate the total number of moles. So that is nothing but you add all this coefficients. So if you add all this coefficient, you will get the total number of moles. Or okay, let me just do this fast. So what you will get, 3.52. So this will give you the total number of moles in the flue gas, of the flue gas. So if you add all this, you will get the total number of moles. Then to find out the percentage of each, let's say for example CO2, you need to take that respective what do you say, stoichiometric coefficient or the moles for that particular uh, the gas, and then you need to divide it with total number of moles. So 3.52 divided by total number of moles, this times 100 will give the percentage of CO2 in the flue gas. So like that you are supposed to calculate for all the gases that you get here except for the ash. So this will be the total number of, this will be your composition of the flue gas. You can complete the table, or I will complete it and I'll post it in the, or while uploading I will calculate it and post it. So before we conclude, let's just solve. Actually, all the three are very simple. So let's just solve one or two question, or we can take up in the next class. But at least solve. Let's solve one of the question. So this is like, just repeat the calculation. Calculations. Sorry, calculations for. Yeah, it might be because I don't know the total number of moles. So based on that, it will vary. So again, it just, so once you get to know for CO2, for H2O, it will be 2.89 by total number of moles into 100. Similarly, if you see for oxygen, it will be 1.071, or you can say percentage of excess of oxygen, it will be 1.071 by total number of moles into 100. So yeah. So let's just solve one more question. It's a very straightforward, simple one. So you have a municipal solid waste weighing 1 gram. You are heating it at 105 degrees Celsius for 24 hours. Weight of the dry material is found as 0.9 grams. So this you are going to heat it in a furnace at 950 degrees Celsius for 7 minutes in the absence of air by putting the lid on the crucible. The weight loss is found as 0.35 grams. The remaining material, whatever you get as a resid, like that that 0.35 grams, is cooled, and when the temperature reaches to the ambient temperature, its lid is open and is further heated in an oven for half an hour in the presence of oxygen. After cooling the material, the residual mass of the material is found to be 0.14 gram. Determine moisture content, volatile matter, ash percentage and fixed carbon of the waste. So I hope you know everyone is able to understand what kind of processes is happening. So if you see, initially this 105 degrees Celsius for 24 hours is for drying. So in drying, the primary the primary thing that gets removed is your moisture. So that is the reason. So yeah, so once you treat it into this process, all the moisture will be removed, and the weight of your dry material was found to be 0.9 grams. So from here you will be able to identify what is the moisture content of the sample. What is the percentage of moisture content? Anyone? 10 percentage, yes, that's correct. So it is nothing but 1 minus zero point 0.9 by 1. This times 100. So that will be 1 percentage. So next you have is your once you do this, oh sorry, 10 percentage, thanks. And then once you do this, what you are going to do is you're going to heat it in a furnace at 950 degrees Celsius for 7 minutes in the absence of air. So during this process, all this volatile matter that you have will get removed. So the volatile percentage is nothing but whatever is going to be left out will be the what do you say, percentage of the volatile matter. So that will be 0.35 by 1 times 100, that is 35 percentage. And what about percentage of ash? 14%. Point sorry, 0.14 time by 1 times 100, so that will be 14 percentage. And the final thing is your percentage of fixed carbon. Now how will you evaluate the percentage of fixed carbon? You know three values, you need to calculate the fourth value, but not, you don't have any, like it's not direct. Yes, percentage of ash is 14 percentage. Now I'm asking for the percentage of fixed carbon calculation. So when you burn a municipal whatever waste or biomass, these will only they are these are the four quantities: your fixed carbon, ash, volatile matter, and moisture content. And how did you calculate this 41 percentage? Yes. So whatever the remaining will be percentage of fixed carbon. So this will be nothing but 100% minus percentage of volatile. Let me write it in sequence: moisture plus percentage of volatile plus percentage of ash. So this will be nothing but 100 minus 10 plus 35 plus 14. So it will be 100 minus 59, I suppose. So that will be 41 percentage. So this is the percentage of fixed carbon. So I hope this is a very straightforward question. There are not there are no much kind of discrepancies with the answer. So we have two more questions, but I don't think we have time. And again, these two are very straightforward, so it will not take beyond 10 or 15 minutes. So let's take up that in the next class. So if you have any doubts, you are welcome to ask me right now. Let me just stop sharing my screen. Okay. Yeah, sure. Mm. Mm. Yeah, so this, yeah, go ahead. Yeah, so this is based on the standard procedure. So yeah, you're correct. So depending upon the material, the what do you say? The temperature at which all the moisture will be removed will be different. But for biomass or the other waste sample, this is set as a standard 105 degrees Celsius for 24 hours. So what they take under consideration is once you do this process, almost all of the moisture, whatever is present within the material, will be removed. Yeah, exactly. So all these are standard, this thing which is set by the, which are set parameters, what do you say, set standard conditions for doing this analysis. Okay. So, yeah, okay. So, if nobody else has any other doubts, let me just ask once again. Do you guys have any other doubts? If Are there any doubts which you want to ask me right now? So if you don't have any doubts, again, if you have any doubts, then please post your queries in the Q&A section of your in the course page, so we will be able to address to those questions. And I will also provide my email ID, which so in case if you have any doubts, you are always welcome to email me. I will reply to you as soon as possible. So yeah, sure. So I hope you guys, everybody is able to access the recordings as well as this presentations, whatever I'm uploading. So in case if anyone is not able to access, then let me just explain it again. So in the course web page, the main course web page, towards your left hand side, after the week's session, you will be having a column for you'll be having a row wherein it will be written as problem solving session. So if you click on that, you will be directed to a Google spreadsheet through which you can access the recordings of this lecture as well as the presentations. So yeah, let me just conclude the session for today. Thank you everyone for joining the week 3 live interaction session. Our next session will be on 16th February, week 4 live interaction session. So till then, hope you are able to comfortably solve the assignment. So happy learning and thank you. Bye. Yeah. Uric acid.